Welcome to ECC web seminar. This time I will present the run analysis, sensitivity analysis of distillation plant, critical equipment case study. This case is very interesting because this run analysis was performed to support the decision for maintenance manager which equipment they need to invest during the program maintenance time in distillation plant based on a limited budget. So we performed the run analysis, we defined which were the critical equipment that impacts more the distillation plant production efficiency, and then based on the list of equipment criticality, the maintenance team is trying to implement the improvement actions for the next distillation plants campaign. My name is Dr. Eduardo Calixto. I'm ECC CEO founder. I'm CRP Certified Reliability Professional, Certified Functional Safety Expert, Automotive Functional Safety Expert, and have more than 25 years in projects for oil and gas, railway, aerospace, and different organizations across the globe. So here, just to demonstrate one of the components that I work with and I work for during my professional life. So we have some common definitions here. Operation availability is uptime divided by total time. Production efficiency, total production for nominal production. Reliability, the chance of equipment to operate under defined operation condition till a specific period of time. RE is the percentage of substance or equipment reliability impact in a system reliability. So we have also other index such as failure critical index, a percentage of equipment or component of system total number of failures. Down event critical index, percentage of equipment or component number of system shutdowns. Downtime critical index, percentage of equipment or component number of system downtime. And production loss index, this is the percentage of system equipment of total system production loss. So I will present some of index as a result of critical analysis parts of run analysis. The previous video I presented the methodology of the run analysis. So the first step here is to scope definition. You already spoken about the scope definition of this run analysis distillation plants. So we got all information necessary to perform this run analysis. We PAGs, the documentations related to the plants, also maintenance documentation. Then we perform lifetime data analysis, basically based on field data, historical data. We're trying to perform predict the reliability of each equipment and critical equipment. Then we the next phase, since we have the probability density function and repair time, probability density function for the repair time for all equipment distillation plants, we perform the run analysis of the RBD model. So we model the whole distillation plant, and then we perform the simulation for 5 years. And then of course we based on the failures that based on the profile of each equipment, that will define what is the production efficiency and operation availability that the system will achieve in the next 5 years. And then based on it, we jump to the next phase, that's critical analysis, and define which are the critical equipment that's most impacting in distillation plant production efficiency and operation availability. And then of course by knowing this equipment, that comes our recommendation, and we have performed the sensitivity analysis here to define what will be the distillation plant production efficiency and operation availability if we eliminate these failures that we in this critical equipment that's more impact the distillation plant. And then in the end we have a conclusion, and we will see the part of sensitivity analysis how much money we can save with small, theoretically small improvements in each critical equipment. So the RBD model, some important information here. The RBD model, we have basically two configurations in series when the equipment itself causes direct impact in the system, and in parallel when we have redundance. So usually we have here for parallel configuration standby configuration for pumps, and of course some heat exchangers. And because of that, in many cases, these pumps, despite have a high number of failure in this 5 years campaign, they will not impact in the whole system. And that's different story for the static equipment such as the tower distillation, the vacuum distillation tower, and also the furnaces that would have a direct impact because they do not have redundancy. It's not common as well. They have a direct impact on the whole system. That these are those equipment that's in the end supposed to be improved. So performance requirements for this distillation plant minimum, they need to achieve 90.8.2 production efficiency average in 5 years. And the objective of this run analysis defined before is to define critical equipment to be repaired during program maintenance in order to assure that the distillation plant will achieve this 98.2% in the next campaign. And then, of course, we have a limit budget for implementing this maintenance program, and the run analysis supports the maintenance team in the directions to give them a clue which are the most critical equipment that impact on a distillation plan, and based on it they have a list from the top critical equipment that they need to focus, and that is the priority of the budgets. And then, of course, once we achieve the budgets, we will make improvements when new budgets, new money investment is available for our plants. So very important step is to perform the lifetime data analysis. So before model the RBD, reliability block diagram, we collected the historical data, field data, and then we, based on it, we predict the reliability for each equipment. So here we can see the one probability density functions that we see that there are after 1.15 years there are very failures, early life failures, and that is defined for this beta. This is lower than 1, we can see here, and then we expect a 63% of chance of failure after lower than 1 year, 0.088 years. So, and that's the profile of the furnaces. What's happened in this furnace was coke formation during high temperature, and also because they input some heavy oil in this distillation plant, and that was by doing the root cause analysis was the reason. And then after that we need to change the material in these furnaces, and this was the one of the critical equipment that we'll see later on. Then of course we have here for the furnaces, we have the probability density function. As I mentioned, we have the expect time to failure usually, and we have the repair time. So we can see that we have very high repair time for the two cases when we have coke formation, and that's why these furnaces are critical for the plants. The beginning was just an example. By looking on a lifetime data analysis result, we can already have a clue how critical are the equipment. But of course, when we start to model the system in RBD, this is the first level. We have 9 systems here. So if we lose one of the systems, the distillation plant will shut down. Then of course, inside of each block there are a combination of different equipment. So here below, this figure here was produced in the block sim from last software. It's very good to look on the operational availability, reliability, and very detailed information about how much I can get improvement in my system when I improve specific critical equipment. And then in addition, we model that in the Maros DNV software to look on the production. And in this time, this block scene had no production. Possibility to include production here was very simple. Production for only one product, and then of course in distillation plants, in the refineries, the distillation plant is the one that gets the crude oil and splits this crude oil in different products, such as diesel, gasoline, light products, and so on. So, and then we have as output different products. That's why we also use, in this time we use this DNV software that's fit for production. So when you start to look on each reliability block diagram for each one of these systems here, we'll see, as I mentioned, that we have different redundancy here. So here, for example, we have 3 pumps, 2 out of 3, and we have 4 lines of these components here that are heat exchangers. So there's a huge number of redundancies. So then we have the salt treatment also. We have the salter here, a lot of redundancies. Because of this redundancy, there is no impact on system operation availability and production. In some cases, we capture some pumps, for example, that have impact, direct impact, but actually the critical ones, as we will see later on, will be the furnace and the tower distillation and the vacuum distillation tower. So here the heating system again with different configuration of heat exchanger, and then we go on. Here is a prefection subsystem. We have atmospheric distillation. So atmospheric distillation we have here. You can see in red, this is the furnace that's triggered. It's one of the critical system, that's why it's red. Then of course here we have water system was not critical, and also diesel treatment system also not critical. So by perform some the simulation for 5 years, so we get the production efficiency as 97.678%. That is below this 98.2. So, and then our next question is to try to identify which are the critical equipment. So this result here basically is the production, and then of course, as I mentioned before, we had both the reliability block diagram. We want to look on in terms of production, in terms of reliability. So by look on reliability, here we have the graph that shows static reliability importance in 1 year. So we can see the vacuum distillation system is the critical ones, and then when you look on the vacuum distillation system is the furnace and the tower, vacuum distillation tower. There are 2 equipment that I need to improve. So it's very interesting, this graph, because they shows the red color is the one with the lower reliability, and the one that I need to focus to improve. So meaning, if I improve 1% in the system, I will be improving 4.6% of my system. Then when I look on a production point of view, I can see that the 2 furnaces, as I mentioned here, and the tower, atmospheric tower and the distillation tower here, are the ones that have 50, almost 70% of the percentage of total loss of production. These are the 4 equipment that I will focus on. So by looking on it, now we have here the distillation, the tower distillation. So in tower distillation, if we expect that we can, by eliminate the corrosion inside this tower distillation, by changing the material, we can improve 37%. So I expect time to failure, mean time to failure goes from 8.83 to 12.16 years. So internal corrosion parameters that we measure, that was the problem in this tower. They have the beta, these are parameters of viable. So basically we found that they have the beta in a very early phase, and the 60% was in 5.6 years. And then of course we expect by changing material, we will not see, we have 100% reliability in 5 years. So that is this location parameter in the viable 3 parameters meaning. So that means we understand that by changing material in this tower distillation, we will not have in the next campaign this corrosion. So we improve 0.12 production performance in vacuum distillation, And that's it's only in the vacuum distillation tower the efficiency, the production efficiency will increase from 994.474 to 995.993. And then of course the impact on the plant, distillation plant, will be 18%. Then we go from 98.776 to 6298.803, and we are saving this loss that we are saving here is 1 million, around 1 million. So we can go now for the tower distillation itself. We have vacuum distillation, tower distillation. So basically the vacuum distillation, they separate, they come after the tower distillation, and they separate the heavy products, and both are critical. So here the tower distillation, we have very similar PDF, again beta very low, below 1, and that shows early life failures, again caused by the corrosion. So we have corrosion in both towers, and we propose to change the material, and here is the same case. We expect to have, by changing the material, we will not have this corrosion and shut down the plants. And then in this tower, the production efficiency will improve from 99.524 to 99.737, and then we have 0.21% of increase in production distillation. So we increase in 98.726 to 98.803. So again, 1,200,000 saving lost. And again, in the furnace, as I mentioned before, we also measure. So here, beta parameter beta lower than 1. We have early life failures. We have 63% of failures occurring earlier than 1 year, and 0.88 years. And that's take place in after 1.15 years. This is the picture that I shown on the very beginning when I was talking about lifetime data analysis. And then of course, what you expect, that we have not the scope formation, and during the next campaign, if we are putting a proper operation procedures and also materials in the coke formation. Then of course we have a very increasing 0.24 increasing in the production efficiency for the furnaces inside the vacuum distillation system. And then of course in distillation plant we increase from 98.7627 to 98.944, and then we have in the end the improvement of which was saving 1,800,000 in 5 years by improving implementing this solution. It's important to notice that we need to implement the improvement in all this equipment. That's a very important aspect. We need to have in mind that in case of reliability, the system reliability will be lower than the lowest reliability. So that's meaning if I improve the two towers, the vacuum towers and distillation tower, but not improve the furnace will still will keep the production efficiency of the distillation plant lower than 98.2%. So I need to improve the three system. And then of course that's the most of the budget was focused on this investment for this three critical system. Then of course some critical pumps was also considered. So you can find this case study on my bestseller book, Gas and Oil Reliability Engineering, and this case is in page 335, and there is a chapter of run analysis, chapter 4, and this is case 4.6, and then this case explains the system. So you can visit also the website. You can get more information in papers and information about the training, information about reliability database, oil and gas database. We have FIMEA database, RCM database, and reliability maintainability database. Also very useful for produce this type of run analysis, since I have a lot of experience in the previous project in oil and gas. So I developed this database that can support for new plants in case you have no data available. And then, of course, we provide consultant service and training. So thank you for your attention. Keep it tuned in our YouTube channel. We'll present new run case studies for the next web seminar. So see you in the next seminar.